And he has been working with on different things, including DAC, and he has been working on modeling the clustering of the galaxies for Addison. We have been working together for like a couple of years, and this is the first time we see that's truly 21st century collaboration.
Thanks, Amir. So this talk's about the work I've been doing over the last 2 years as a PhD student in Oxford. And I've worked with mainly two groups. So first of all, ACT, which is a collaboration that Amir and also Dick and others here are working on as well. And so for anyone who doesn't know, this is a small-scale CMB temperature and as of next year, polarization experiment based up in the Atacama and led by Lyman Page over in Princeton. So most of these collaborators are stateside, but everyone else with this, my supervisor, trying to definitely mention me. And I'll go on to talk about some more recent work towards the end of the talk that I've been doing with HerMES, which is the Herschel Multi-Tiered Extragalactic Survey. So we have this slide with a ton of names on. People I've already been working with are Marco Vieira, who is a postdoc in Caltech, and Lingyu Wang, who's a postdoc in Sussex. So I wanted to start my talk just by sort of going through an introduction to CMB cosmology. I think everyone will know this, but it's maybe not such a bad idea to talk a little bit about it anyway. So right now, the CMB measurements of the CMB temperature, or I guess more correctly, the CMB temperature anisotropy, are providing vital constraints on cosmological models. And the simple idea is that there are photons that are leaving this essentially two-dimensional surface a couple of 100,000 years after the Big Bang, and have been traveling through space largely unperturbed to our telescopes and detectors since then. And imprinted in those photons is information about the process that happened very early in the universe and what the distribution of matter in the universe was like before there was any complicated structure formation. So this is, right now, an absolutely vital probe that we have to constrain cosmology. And because those initial conditions early on in the universe that lead to the Gaussian or very near the Gaussian, the statistic of choice for studying the CMB temperature fluctuations is the angular power spectrum. So again, I think most people are probably familiar with this, but I have a number of these power spectrum plots, so I think it's worth maybe just quickly talking about what I've plotted, or what's plotted. So on the x-axis, this is the spherical harmonic multiple moment. So this means that large angular scales are over up towards the left of the plot, and smaller angular scales down towards the right. And this is a two-point correlation function. This structure here is what we use to infer cosmological parameters. So for instance, this first peak tells us about curvature, flatness of the universe. The ratio of the second to the first peak tells us something about how much baryonic matter there is in the universe, and so forth. So this is a plot taken from the WMAP team, and WMAP had an angular resolution of around 13 odd minutes, which means that you can push down to a multiple of around 1,000. And I'm going to be talking about some work that's been going on probing the CMB temperature anisotropy at small scales. So although this isn't really a primary CMB sort of cosmology talk, I wanted to include this slide with some of the motivation for looking at the smaller scale CMB. So as I said, in those photons from the surface of blast scattering, there's information about the distribution of matter in the early universe, and we're interested in constraining the primordial matter power spectrum. And in the concordance cosmology, we parameterize this with this index, the spectral index NS. And so this plot over here is an exaggeration. I mean, our constraints on this parameter are way tighter than shown here, but the idea is just that we can use measurements on small angular scales to complement the measurements and constraints we have from large angular scales to improve constraints on this parameter. And why is that interesting? Well, we can connect this parameter NS to the inflationary potential and thereby constrain inflationary models. So the idea is we combine measurements of NS with, for instance, the tensor to scalar ratio R and constrain regions of inflationary parameter space. And this has already been done and will continue to improve as constraints in these parameters. So like I said, this is just a little motivation for looking beyond where double map gets us to the smaller scale CMB anisotropies. Some other motivations for doing this include looking at early universe phenomena such as cosmic strings and trying to improve constraints on the number of relativistic species. Also, I guess, signatures of constraints on early dark energy models and so on. Now, when you look at the small scale CMB, so beyond where WMAP got us, which ACT and SPT, South Telescope, and also Plancker are involved in doing right now, you run into a problem, which is that your measured power spectrum starts to be dominated by non-CMB components, which we call foregrounds, on the basis that the CMB is its background from this very high redshift surface of our scattering, and most of this other stuff is in between us and that surface. So plotted here are 3 sets of data points from ACT. So we have one set up here, one set in the middle here, and one set down here. And these are the 3 power spectra from correlating the ACT maps at 148 gigahertz and 218 gigahertz. And then the middle spectrum is the power spectrum from cross-correlating one map at each frequency. And the idea is that this red line shows the primary lens CMB, and it's plotted in units so that this is the same for each frequency. And you can see that the data points on these small scales of L of a few thousand, so this is pushing down to scales of a few arc minutes. We're seeing power way in excess of this primary CMB signal. And so if we want to get at that CMB signal and constrain the cosmology in the way I was just talking about, we need to understand these other contributions and subtract them. So in simple terms, we have contributions from radio sources, from this near Soldovich effect, we have scattering of CMB photons by Os electrons in clusters, and then from what's labeled on here is IR sources, which is going to be what I'm going to talk about for the rest of the talk. So the thing to take away from this is that to constrain parameters, to constrain cosmology at small scales, these foregrounds become a big problem. Okay, so what are these IR sources? Well, we believe that these are galaxies that are very distant, with star formation rates that are an order of magnitude or more greater than that in the Milky Way. So star formation is very active, and the idea is that these young stars are enshrouded in dusty disks, and the dust grains absorb the starlight from the young stars and then thermally re-emit it mostly in the rest frame far infrared. And because these galaxies are very far away, cosmic expansion then stretches the wavelength of these photons. So they're sort of millimeter band, a couple of hundred gigahertz frequency-wise, and are picked up in the bands of our CMB experiment. So these galaxies are, with the angular resolution of ACT and SPT instead of Planck, these are basically point sources. But something that's very important to emphasize is that we don't actually resolve these objects at millimeter wavelength. So they're below, they're too faint to actually see them in our maps and subtract them that way. So this is effectively a diffuse background. Obviously, if we could see all these sources, we could just mask out the little points in the maps where they were sitting and then calculate our power spectrum and look at the CMB cosmological constraints, no problem. But that's not the case. These are all faint and below our noise limits. And the key thing about these dusty galaxies and why they're interesting and also potentially a big nuisance is because they're very strongly clustered. So I'm sure you've all seen these beautiful pictures from embodied dark matter simulations where you have this intricate filamentary and node structure of dark matter, this cosmic layer, these regions, these void regions, which are very empty, and then these very dense filaments and so forth. And so these galaxies, like all galaxies, are in some way tracing this underlying dark matter distribution. And what that means is that they tend to clump together. They're not uniformly distributed on the sky. If they're uniformly distributed on the sky, in a sort of a Poissonian process, then the contribution to the angular power spectrum, which you're trying to measure to extract the CMB signal, wouldn't have any scale dependence. It would just have a flat shot noise term. And if that was the case, then subtracting this dusty galaxy signal from the primary CMB would be very easy, just on the basis of that angular scale dependence. But because of this clustering, because these galaxies are living in clumps, that's not the case, and there's a scale-dependent contribution which we need to understand. So this is why studying these objects is interesting from a CMB foreground point of view. And here, Graeme. So one thing I wanted to emphasize is just that the angular power spectra of these dusty sources has actually only very recently become available. It's only in the last few years that this sort of data has really come in. So firstly from Spitzer at 160 micron, and then BLAST a couple of years ago in the submillimeter, and then in the CMB bands from SBT, Subpole Telescope, and then ACT. And there's then been several more papers with much improved data from Herschel's Spire instrument and also Planck earlier this year. And there's this real increase in data over the last couple of years, and that's going to continue for the next few years as more data is produced from SBT, from ACT, from Herschel, from Planck. So there's going to be a real explosion of these angular power spectra containing the signal from these dusty galaxies. So I want to go on to talk now about some work that I did, which Amir here was leading last year, and that's to do with cross-correlating maps from two experiments, from ACT and BLAST. So since I hadn't shown a picture of ACT before, I thought it was worth sticking one up. So this is ACT. It's a 6-meter telescope up in the Atacama in Chile at about 17,000 feet. And the maps that we're using, as I mentioned before, are at 148 and 218 gigahertz. And this experiment, BLAST, it's a balloon-borne experiment. BLAST stands for Balloon-Borne Large Aperture Submillimeter Telescope. And this balloon flew over Antarctica in several trips and made maps of the sky, or took data that was made into maps at 250, 350, and 500 microns. And there's a small area of overlap around 8.5, 9 square degrees between the fields mapped with ACT and the fields mapped with BLAST. And so the question is, what do we get if we cross-correlate these maps from these two different experiments at this quite considerable range of frequencies? What is the power spectrum that we see? And this is interesting for the purposes of these dusty galaxies, because in the submillimeter, in the sky that BLAST sees, the CMB is negligible. The CMB contribution is very tiny, and similarly, things like this in the High-Redshift effect and the radio sources, their spectral dependence is such that in the submillimeter bands, their contribution is tiny. So all we're seeing, the dominant extragalactic signals from these dusty sources. So the question is, to what extent are the sources that are dominating the signal in the submillimeter are also the same sources that are a CMB foreground in our millimeter bands? So this plot's going to be hard to see from the back, but these are power spectra from calculating those correlations between those different maps. So there's a few things going on here, so let me kind of talk you through what's shown. So firstly, you remember that in those earlier plots, so the ACT plot and then the first W map plot, I had multiple moment on the x-axis, and then I actually, well, what was plotted was not the power, but basically L squared times the power. So unfortunately, there's a kind of a convention issue here. So these plots are not on those same scales. This, on the x-axis, this is essentially L. The scaling is the same up to some constant factor. But on the y-axis now, I don't have that factor of L squared. So what that means is that anything that doesn't depend on angular scale is actually flat on these axes, whereas it would be tilted up on those axes I was showing before. So in terms of L range, the data points that are plotted on these panels are going from something like L of 1,000, so that's about the limit of W maps, where W map can push up to, down to L something like 9,000. So that's angular scales of a little over 1 arc minute. So what are all these panels? These are power spectra. These triangles here are power spectra calculated from correlating BLAST maps with BLAST maps. So on this diagonal, you have the 3 auto spectra, 250 correlated with 250 micron, 350, 350, 500, 500, and then the 3 cross spectra. But the thing that I want you to really look at are these 6 panels over here. So these are the spectra we get where we correlate the 2 ACT maps at, and I also apologize for switching between wavelength and frequency all the time. But this is 220 gigahertz, or 1.4 millimeters, and 2 millimeters, or 150 gigahertz. So these 6 spectra are what we get, and as you can see, we're not drowning in signal to noise, but we do have a significant detection of not only this flat shot noise component, but also some scale-dependent clustering, which was this important feature of these galaxies that I was talking about a couple of slides ago. So, I mean, most of the signal to noise, I think, is in this spectra down here. So this was confirming, what was expected, in that, to some extent, those sources which are dominant in the submillimeter sky are also those sources that we're seeing CMB experiments. And so this is very encouraging. It suggests that perhaps we can combine measurements in this millimeter, where studying these objects is far easier, with what we get in our millimeter bands to try and constrain the contribution to the angular power spectrum from these special sources. So this is work I went on to do following the work I've been doing with EMEA, and over the summer I wrote a paper where my aim is to construct a simple template for describing the scale dependence of this clustering component as a CMB foreground. So this isn't a physical model for what these galaxies are doing, it's a phenomenological approach to try and subtract them from the CMB signal. This plot here just shows angular power spectra of these distant sources from a range of different experiments. So these green points on, which are lying on the smaller scale, so I'm back to positive multiple moment, I apologize for switching. These three the green points in these three panels are from blast, so those were shown in the plot before. These four sets of blue points are from Planck, so this is data that was, came out beginning of this year. And something I should say about these Planck points is that these are only, or if you believe the Planck data reduction and processing, this is just the contribution from these distant galaxies. And obviously, at 220 gigahertz, and even 353 gigahertz, contributions from the CMB are important as well. But what Planck did for their early data release is kind of the opposite to what they're going to do eventually. They used their wide frequency coverage to actually get rid of the CMB from these spectra. So ultimately, the reason why Planck has all these frequency channels is so that they can use that to get rid of the non-CMB components and go after cosmology from the CMB. But for this early data release, they did the opposite. They got rid of the CMB and just pulled out this contribution from these distant galaxies. And so all I want you to notice here is that we're plotting power spectra over a range of around a factor of 5 in frequency. And there isn't really, there doesn't, by eye at least, seem to be a strong evolution in the shape of these spectra, even over this wide range of frequency. And so, encouraged by this, I tried to fit a very simple model to describe the clustering of these sources, where the clustering power varies just as a power law with multiple moments, so angular scale, and then the frequency dependence is given by the square of this modified black body, and this is squared because the power spectrum is a two-point function. And so the parameters I'm constraining are this index here, this emissivity index, and then this effective temperature. So I should highlight that I'm not constraining the dust temperature of these actual galaxies by doing this. What I'm saying is that all these galaxies taken together, the frequency distribution of the total power can be described by this modified black body. And you may ask, well, is that guaranteed to be the case, even if individual sources can be described with this modified black body? Why should their composite, why should this form work with their composite? And it's true that this isn't, it's not clear that that would be the case. So my choice of this form was just motivated by the fact that this form does work for the intensity of the cosmic infrared background, so the 1 point function, just the total flux from all these sources that we measure, for instance, with FIRAS. And so it's a slight sort of, it's a stretch maybe to say that the clustering should be related to, the frequency dependence of the clustering should be given by this modified black body too. But that's what I went with, and it seems to work very well. So let me show you this model fitted to the data. So these are the same Planck and glass data points that I showed in an earlier plot. I actually fitted for and subtracted out the shock noise. So remember, the shock noise is that scale-independent Rossonian contribution, which just comes from there being some finite number of sources in any given patch of skyline I'm observing. So this is just the cluster component. And this red line has the same power law in each band. And for doing this simultaneous fit to the two instruments, I obviously had to account for systematics like photometric calibration, uncertainty, the filter profiles, and so on. And when all this is done, you see that the data points lie very convincingly along this single this line with the same power law index. So this is pretty remarkable. Why is it that this simple power law dependence works so well over this huge range of angular scale? So don't forget, this is basically 2 decades in angular scale and a factor of 5, as I said before, in frequency. So this is something which I wasn't really expecting. It's obviously very nice if you're interested in subtracting this contribution from your CMB, right? Because you have a very nice a simple template that you can use with your cosmological parameter fitting. And so, oh no, sorry, let me show this plot, which is looking at the frequency dependence. So this is, these axes are a little small, I apologize for that, but on the x-axis we have frequency. This green, this blue band here shows the square of the modified body that was the frequency dependence in my model. And so you can see that by combining the Planck and glass data points over a wide range of frequency, we get a pretty tight constraint on the size of the clustering power with frequency. And then these boxes, these aren't actually data points. These are, on the x-axis, the full width half maximum of the filters of these various experiments. So the reason I showed this is because something that I don't think people had maybe realized is that your filter shape is really important when you have such a steep increase in the frequency of this cluster power. So if you look down here at the Planck 143, ACT 148, or SPT 150 gigahertz, you can see that the cluster power is varying by around an order of magnitude as you go from one side of the filter to the other. And what this means is that if you're trying to compare, for instance, the cluster power you expect from ACT at 218 gigahertz with the cluster power you're going to measure with SPT at 220 gigahertz, even though those two nominal frequencies are very similar, you can actually, because of this very sharp frequency dependence, there's something like a 30 or 40% difference due to the shape of the filters. And I think that's something that I certainly certainly hadn't occurred to me. You know, I just looked at numbers from ACT and numbers from SPT and compared them directly without thinking about the implications of this frequency dependence.
So the shape of this depends on your power law and the frequency dependence of the calculation?
Right, so there's a degeneracy between the parameters that describe the blue curve and the index, yeah. And obviously you know, if it wasn't a power law, then I'd need some extra numbers to talk about this amplitude. But as it is a power law, it's just this single number in each frequency.
So how does the angular power law compare with the naive expectation of cluster in another galaxy?
Right. So it's consistent with the angular correlation dependence of populations of galaxies that we see with SDSS or quasar. Well, it's consistent with the naive galaxy clustering expectation. Yeah, things are a bit more complicated because these sources are.
Well, when you talk about this subclass of galaxies,
yeah,
are we referring not only to the sort of relative amplitude? So there's some comparison from the.
Okay, so this is an important point. So there's a distinction between looking at the correlation function from the resolved sources and looking at the power spectrum. So here, in the power spectrum, these are all unresolved sources. So everything's weighted by flux. Right, I don't actually know how many of these things there are, so it's a slightly different ballgame. And I'll get back to that. It's an important point which I'll come on to. But for now, let me just sum up this first part of my talk. So I've been talking from a CMB cosmology point of view about these sources. So we're looking at the CMB cosmology beyond the scales that were proposed by WMAP, going down to these small scales to try and constrain things like the primordial power spectrum and inflationary models. Foregrounds such as these dust galaxies become dominant, we have to understand them and subtract them. And this potentially problematic foreground of the dust galaxies actually looks like it's maybe not so bad in terms of its frequency and angular scale dependence. It seems like this very simple power law that does a good job of describing it. So now I want to take off my cosmology hat, if you like, and put on my astrophysics hat, and think about a couple of questions that arise from what I've been talking about so far. So first of all, what can we learn about the physics of these dusty sources from the angular power spectrum? And what is the physical origin for this very nice power law that seems to be there? So before I go on and talk about some work I've been doing with the HerMES, the Herschel collaboration, I wanted to mention a problem that comes up with looking at these sources in some millimeter and millimeter maps. So as I said, we don't resolve these sources in our CMB bands, but even in the Herschel bands, the Herschel Spire bands, at 250, 350, 500 microns, we don't resolve many sources. And the problem is not that they're too faint, but because there's a very large number of them for the area of our experiment's beam. And so this is something called the confusion limit. And this is demonstrated quite nicely here. So this is the same area of sky in 9 different frequencies. So we're going from sort of near infrared, mid infrared, far infrared, up to some millimeter. And this is this patch of sky as seen by Herschel's Spire instrument. And you can see that there's simply a lot of structure that we're not able to resolve because our point spread function, our beam, is too big. So unless we have some huge whopping source, we can't say whether this is one object or several objects. And so this limits our ability to study the physics of these objects by actually resolving them, pulling them out, having follow-up multi-frequency data taken on them, and so forth. And so for this reason, looking at statistical properties such as angular power spectrum I'm talking about is actually very important. And your resolved sources, these whopping bright ones, which are sufficiently bright that you can pick them up even with this confusion problem, only account for a small fraction of background intensity in the spy bands. Okay, and I put together this slide very quickly to just talk about a little motivation for trying to understand these dusty galaxies. So these dusty galaxies, as I said, have very high rates of star formation. So by studying these galaxies, one would hope that you're in some way probing the star formation history of these sources of lying at a wide range of redshift. And from multi-frequency surveys of small patches of the sky, we seem to see this very strong redshift evolution in star formation rate. So star formation is not happening in the local universe in the same way as it is at redshift 1 or redshift 2. So the situation seems to be that these luminous infrared galaxies, LIRGs, or ultraluminous infrared galaxies, ULIRGs, are very rare in the local universe, and they're probably associated with mergers of galaxies. In a higher redshift universe, up to redshift 1 to redshift 2, the co-moving number density of these objects goes up by orders of magnitude. They're far more common. There's far more galaxies with enough dust to really produce this intense amount of infrared radiation. And this is a problem which is intimately linked to the downsizing we see in AGN and in other galaxy populations. Right? This idea that large structures are in place at high redshift, which you wouldn't expect if you had a bottoms-up sort of small objects form first and get bigger. A naive expectation from that point of view. And so I think that what this is telling us is that the optimal halo mass for star formation seems to have evolved strongly since around redshift 2, or possibly higher. And so this is motivation for trying to understand these faint dusty galaxies and trying to connect star formation rate and mass. Okay, so what sort of physical model do we use to describe these things? Well, because simulations of star-forming galaxies and so on are currently very limited, these are the sort of simple analytic models that I've been working on and other people have been working on using. So the idea is that this is the power, this is an integral over redshift with some geometric factors in here, and then we have the spectral and the clustering properties of sources that need to go into this equation. So if we take a very simple case of assuming that the spectral and the clustering properties decouple, that is, there's no dependence of the galaxy luminosity on halo mass, which clearly is going to break down at some point, but in that simple idea, we have a factor of the redshift distribution of flux, again squared because the power spectrum is a two-point term, and then we have the three-dimensional power spectrum of the dusty galaxies. And so there's these two pieces which have to go into our model. And so let me talk about something which has come to be called the halo model, which really originated back in the 80s through some work that Dick was involved in, and over the last decade or so has been applied to successfully fit the clustering of many different classes of galaxy. And the simple idea is that while we don't know really what dark matter is, we think we have an understanding of how it clusters, and therefore if we want to relate what we see, the correlations, function of galaxies, the clustering properties of galaxies, to the dark matter that we think we have an understanding of, one natural way to do that is by associating the galaxies with dark matter halos, so these massive collapsed objects, which are the peaks in the underlying density distribution. And this is what the halo model is setting out to achieve. So in simple sort of schematic representation, we go from dark matter to dark matter halos with things like the halo mass function, which is now known pretty well from embodied simulations, and descriptions of the halo bias, which again are measured from simulations. So all this starts from the pressure-exit formulas that have been developed since. And then we have some recipe for applying our halos to galaxies. So it's generally called a halo occupation distribution. And people have been working on different models for this mainly over the last sort of 10 to 15 years. So remember that the power spectrum, or the correlation function, is a two-point statistic. So this means if we're thinking about sources sitting in halos, we have two contributions. We have a contribution from sources which are in the same dark matter halo, so that's this signal of one halo term. And obviously that's going to become important on smaller scales. And we also have a contribution from galaxies living in different dark matter halos, which is called the 2-halo term. And our clustering power is the sum of these two. I wanted to show this one plot, which isn't, it's not like the plots I've shown before, it's not a power spectrum. It's actually the correlation function of galaxies from the main FTSS sample. So this comes back to what you were asking about earlier. So this is the clustering statistic we use for where we have some volume of galaxies that we observe and can count. And this correlation function, or projected correlation function, is telling us something about the probability for galaxies to be found within some certain distance of each other over the naive expectation from them being uniformly distributed. And what I wanted to show you here was that the halo model and this 1 and 2 halo term decomposition has been successfully applied to fit the angular correlation function of these galaxies. So these, the SPSS galaxies are mostly local sort of Z of 0.2 or so, or less. And these two components, the 1 and 2 halo terms, conspire to add together to give this very nearly power law in the correlation function. And I'm going to show later on that something very similar is happening with these angular power spectra. So that power law that I showed before, which is very convenient for subtracting these clustered sources from the CMB power spectrum, arises from the sum of these two distinct contributions, each of which is very much non-power law scale dependent.
Just a quick general question.
Yeah.
What has been done in terms of generalizing this approach to 1 halo plus, say, 2 halos, say 1 halo plus filament? I mean, a filament will give you first approximate.
What was the question again?
What has been done to generalize this approach to the 1 halo plus 2 halo to 1 halo plus filament? Taking a larger scale of
So this,
which will give you a similar excess on large scales.
So I think what you have to hope is that in this simple analytic model, that goes into your description of the halo bias. But I agree with you that it's a big concern that you're not capturing the relationship between the nodes, the massive halos, and the filaments.
Well,
as a limitation of the
it's
model.
just a general question about
Yeah.
whether this has been tried.
It's been tried insofar as people have used catalogs of halos from m-body simulations and then stuck galaxies onto them with some description.
Sure.
Right, which is kind of getting closer to what you're going after. But in terms of analytic models, I've seen some papers, but not much trying to really get at what you're saying. I think it becomes very complicated, right, from an analytic point of
If
view.
you're interested in just the 2-point sphericalized function, which is what's going on here, then that actually is isotropized over. So that the terms that are written have the following assumptions in them. One is that the self-clustering is just Smithsonian, which is incorrect, because there is sort of a self-Smithsonian term associated with the fact that you're dealing with galaxies or halos rather than with the real Smithsonian points. The second, and then there's an important point that's missing in that at PCC, the power spectrum clustering, which is, well, 2 points. Number one is that there's an avoidance of the space that's been grabbed by the other objects. So that's actually not included. The other thing that isn't included is there has been an implicit assumption, it doesn't go, it goes only down some distance, there's been an implicit assumption that this expansion in terms of profiles times number densities of objects actually saturates. There's a residual which everybody ignores, and that residual is actually very important because it guarantees that there is a subtraction term that occurs in order to make everything self-consistent. So that is there at a subdominant level, and that would affect the large scales here, and nobody ever bothers with that term, mainly because most people don't know that there is such a term. But in any case, so there are corrections. Then you can do all sorts of constrained densities in terms of orienting, let's say, the galaxy, and does bring compatibility. So that's saying that I am going to measure objects and I'm going to use more than one parameter. I'm going to use a parameter associated with its orientation. And so that will have an anisotropic correlation function that in fact is a very important fact that's actually reducing from
One could impress what was the PowerPoint correlation.
Oh yeah, but you know, this has sort of been an industry, and there's some of it around CITA for a long time.
Okay, let me push on. Right, so this approach is fundamentally limited, and certainly with better simulations, for instance, and these analytic models are going to be far better. Okay, so to just summarize what I was saying about this halo model formalism, we have these two contributions, two halo terms, which go into the galaxy power spectrum. We have to worry about the number of galaxies and the number of galaxy pairs sitting in halos. And the way it's conventionally been done, this has been done, is through some parameterization like this. So we have three parameters here. One's a halo mass scale, the minimum halo mass to host on average one galaxy. Some other mass scale, the halo mass scale at which we host on average one additional galaxy, generally called satellite galaxy, as well as the central, the first one. And then some power law to describe how galaxies occupy very massive halos, where you have of all the tens of or hundreds of sources, what that relationship sort of asymptotes to. So this is a formalism that has been successfully applied, despite its limitations, to the clustering of objects seen by FDSS, and so not only the FDSS main galaxy sample, but luminous red galaxies, quasars, so high redshift objects, Lyman break galaxies, and so forth. And as I was mentioning just a little earlier, the situation is quite different from the angular power spectrum, because we don't know the faint source counts, right? We're seeing everything up to some flux limit rather than everything from some luminosity limit upwards. So it's a very different ballgame. If we're looking at objects over a wide range of redshift, surely we have to worry about evolution in those parameters that take us, that are in this bubble down here, which take us from the galaxies to the halos, especially if we do have some strong downsizing trend. You know, this needs to be allowed to appear in our parameterization. And also, everything gets weighted by flux in the angular power spectrum, so we need to understand the spectral properties of these sources, the actual emission properties of the dust in these galaxies. So this is a far more complicated and difficult problem compared to looking at the clustering of resolved objects. So I want to quickly talk about some work that was done by the Planck collaboration. So this is the paper in which the Planck power spectra I used in my earlier fitting were announced and the data was given out. So this is back to L and L squared CL. So this is the CMB convention, if you like. So these green lines on these four panels with the four different Planck bands, this is now the shot noise. So the shot noise is flat in CL, but gets tilted up in L squared CL. And so what did the Planck team do? Well, they fitted this halo model I've just been talking about, using a simple parameterization that worked for local objects and some recipe for the SEDs, luminosities of these sources. And they found that they could fit each of their bands individually using a fit with a one halo and a two halo component. So we can see that although the large scales on the left in multipole compared to large scales being on the right when we're plotting in terms of a radius, we still have the two halo that dominates on the large scales, and then the one halo which dominates over the two halo, although not necessarily over the shot noise, on the smaller scales. So these orange lines go through the points. That means that this simple model that the Planck team used fits each band individually. But something that was a great concern is that you don't get the same parameters describing how the galaxies sit in halos for the four different bands. So the interpretation presented in the paper, which I disagree with, was that we need a different halo occupation distribution for each frequency. And I don't really agree with this view, because we're talking about thermal dust emission. So we don't have a source that's on at one frequency and off at another frequency. So in my view, if our model correctly encapsulates the spectral properties of sources, then we should have a single recipe for occupying halos of galaxies, because it's always the same population of galaxies over this range of frequency. Right, so this is what we should be looking for. We should be looking to simultaneously fit data from a range of bands. And so I think this is quite an important point. Let me get on to talk, just to finish off, about some work in progress I'm doing with HerMES. So I've been hoping that this work will be finished by now. It's unfortunately taking longer than I expected. But what we're looking at is a total of around 70 square degrees split into several patches, which have been observed with SPIRE. So these are the same three bands that we had for BLAST, as I talked about earlier. And we don't have the frequency coverage of Planck, but we do have an order of magnitude better angular resolution. So the angular resolution of the three Spire instruments are aboard a half an arc minute compared to around 5 arc minutes for Planck. And so this is some in-progress fitting to this new Spire data. So I haven't actually shown data points on here because it's still, it's not public, it's being developed. But this is the model that I've been fitting. And so this, we have the flat shot noise components in each spectra. So these are 3 auto-spectra and then 3 spectra from correlating maps at the different bands, or maps from the different bands. And then the cluster component is split into 1 and 2 halo terms, as I've been talking about. So this blue line is the 1 halo, and the green line is the 2 halo, which, as we know, should dominate in large scales. So a couple of things to notice here, even though there's no data, is something that's quite apparent, is that this power law behavior of the total clustering, that is green plus blue, does look like a power law over a wide range of angular scale. And so, as with the SDSS galaxies, the sum of this 1 and 2 halo component conspire to give very nearly a power law. And so this is where this simple relationship I talked about at the beginning is arising from. Something else to notice is that there's a strong degeneracy over a wide range of angular scales between the shock noise and this 1 halo nonlinear clustering. And so this is obviously a concern. Let me talk a tiny bit about the modifications I'm making to the halo model formalism to try and fit this data. So I talked about this evolution that we think is happening in the optimal halo mass for star formation. So this is actually going into my model as a free parameter. I have some mass scale at redshift 0, then I have some free redshift evolution. And I find that introducing something like this to kind of connect the galaxy luminosity and halo mass and allow it to evolve potentially very strongly in redshift is important for simultaneously fitting the data across all scales and all frequencies. Something I think is important is because these models get complicated and you have a number of parameters, you really want to be constraining them with all the data you have available. So what I'm doing is joint fits to these new Spire data with the Planck data, and it turns out that the Planck lower frequency ends, so the 217 and 353 gigahertz spectra are actually very important for trying to constrain these parameters. Because obviously you need to get the frequency dependence right when you're looking at that wide scale range of frequency. Whereas with just the Spire bands, it turns out you can afford to, your parameters are way less constrained on the spectral source property side. Very quickly, I will talk about some other things that are going into my model. So rather than fitting for a single dust temperature or using SEDs from some model, I'm using a composite SED which is based on observations of the goods field. So this is wavelength, luminosity as a function of wavelength. These grey dots are individual galaxies in this goods field, which has been observed with Spitzer, with IRAS, now with Herschel, so a range of frequencies. These blue points are the binned points that have been binned from these grey points. So these areas are supposed to kind of encapsulate in some way the scatter of the galaxies. And this black line is a composite SED, which has been drawn to fit these points. So what's going on here is that, to a reasonably good approximation, it looks like a single SED does a pretty good job of describing these sources, even though they're lying at a range of redshift, so out to something like redshift 2. And they have a range of total luminosity, so this is just sort of normalized to some value so that they all lie along, so you can ignore the scaling of the vertical axis. But what's important about this is that this is this peak here, by the way, is the thermal dust emission. There's some PAH features down here which are not relevant for the frequencies I'm really looking at. But this black curve here, although a single SED is doing pretty well describing all these sources, it's not a single temperature SED. So you actually need dust temperatures from something like 15 out to about 50 Kelvin to make up this black composite line. And so I think this is important to consider. So people come up with models for a single dust temperature and then try to fit these power spectra. And I think that that's certainly not the way to go. And I think you'll struggle to get the frequency dependence right with that. And this is sort of bringing that up, that you do need multiple dust components.
So all these peaks around 10 microns are PAH?
I think so, yes. And I'm afraid I'm not going to talk any more about those. I'm focusing more on this thermal dust component. Let me talk about one other statistic we can use to help go into the fitting. So I said that there's a degeneracy between the nonlinear clustering, this one halo clustering, and the shot noise over a wide range triangular scale. So something we can use to break that, even though we don't resolve many objects due to confusion limits, is looking at deep number counts from a P of D, probability of deflection approach. I don't have time to talk about the details of this. It wasn't invented to look at these objects, it's been used for decades. The idea is to look at the pixel histogram of a map. So this is flux and number of pixels from one of the Spire maps. And this distribution here has a large Gaussian component, which is basically noise. And the idea is by studying the non-Gaussian tail over here, you can say something about source numbers beyond what the confusion limit. So this is a reconstruction of the source counts. This is dn by ds as a function of flux. And with the deep Spire fields, you're pushing down an order of magnitude further. You're constraining an order of magnitude below the confusion limit, which is out at something like 30 millijoules. So why is this useful? This is useful because the Poisson shot noise component in my power spectrum doesn't care about the clustering of the sources, it just cares about their brightness. So this is directly telling me and constraining my shot noise. And because of this weighting by S squared that goes into the shot noise equation, we're most sensitive to sources that are pretty close to the confusion limits. So this means these constraints are actually very useful for breaking this degeneracy. So this goes in as a constraint on the shot noise in my modeling. So the purpose of these last few slides are just to try and show some of the extra ingredients I'm using as well as the angular power spectrum. The idea of combining different statistics to improve constraints and try and get something useful from these models. Let me very quickly talk about some interesting work which has been done by Lingyi Wang, who's a postdoc of Seb Oliver's at Sussex. And that is a pretty ambitious project combining low and high redshift constraints on star formation, on luminosity functions, and clustering through correlation functions and angular power spectra. So the idea here is that ultimately you want a galaxy evolution model that can fit everything in redshift. And so the work she's been doing is based on some work that Santa Courier was looking at a few years ago on this sort of so-called conditional luminosity function. And there's an extension to the halo model that I've been talking about. So instead of going from dark matter to halo to galaxy, you have some prescription to take you from dark matter to halo to galaxy stellar mass, and then you infer star formation rate using some additional parameters here. And of course, the great thing about this is that lots of our local constraints come from stellar mass limited samples. So if we're going to do a joint fit to high and low redshift data, we need something like this to come in. And so I just put this up to mention, something in the field that's happening at the moment, and I don't think it's near telling us something useful and physical, but I think it's ultimately the way to go to try and understand, galaxy evolution from this point of view. And so let me just say as well that we're not going to say something fundamental about galaxy mergers. We're not going to constrain the physical properties of these objects. To do that, we really need the high-resolution simulations. The purpose of this simple analytic approach is to try and constrain large-scale trends in the population. So, for instance, to see that we need a range of dust components, to see how many dust components we can get away with in some ways, to see do we require a strong evolution in the halo mass which is optimal for star formation. Is that borne out from the data as we'd expect? So this isn't going to tell us lots of detailed astrophysics or gastrophysics. The idea is that from starting from this simple sort of large-scale point of view and increasing the number of parameters in these models, we're going to at some point meet up with simulations on the galaxy scale which are really plugging into the astrophysics and connecting star formation with galaxy mergers and so on. So this is not going to completely describe the physics that's going on. It's just going after these large-scale sort of simple trends. Let me finish by putting up a slide with some future data that's going to be coming out soon. So the ALMA revolution is finally upon us, and what this is going to mean is arc-second resolution submillimeter images. So the purpose of ALMA is not to make these maps to calculate the power spectra, but to really go after pointed observations of, for instance, a group or galaxy cluster containing these dust and shrouded star-forming galaxies, which we've never been able to actually see before. And of course, this is great for looking at the relationship between these objects and possible galaxy mergers, the distribution of these objects within groups and clusters over a range of redshifts. So this is a very complementary view of these sources to what I've been talking about. Also, there's a bunch of cross-correlation studies correlating the sources that make up the infrared background that I've been talking about with other objects that are tracing large-scale structure. So I don't have time to say more about this. This is extremely interesting. You can imagine that if I have two traces of large-scale structure, I can come up with ways to cross-correlate data sets which can constrain the properties of both. So, a quick example, let's say I have an object with a known redshift, like a quasar catalog. I can cross-correlate that quasar catalog with my maps of my unresolved dusty galaxies and try and pin down, for instance, large-scale bias in these objects as a function of redshift, which is very hard to do from my power spectra alone, right? Because I'm seeing this integrated sum of contributions from redshift 0.5 up to redshift 4, depending on frequency. So these studies are going to be great for constraining the dusty galaxy properties and breaking some of the inherent degeneracies that we get at just looking at the angular power spectrum. And also improvements on the high redshift dark matter halo properties is something that I think is going to be useful. So for instance, I hadn't realized this, but it seems like the small-scale biasing of the dark matter halos of sort of 10 to the 12, 10 to the 13 solar masses at redshift 1 and 2 is actually not known particularly well. And you can imagine that this is critical to using this halo model, to making the galaxy to halo to dark matter connection. We need to know those dark matter halo properties. And that I'm informed that there's some improvements over the next few months, simulation-wise, which can help us do this. So that's all I had to say. Just to sum up, this power law we see in the angular power spectrum in our CMB bands holds as well. This power law holds over a range of frequencies, and it's great if you're trying to subtract these dusty sources from the CMB. Within that simple power law, there's a lot of interesting astrophysics, which we're trying to get at through studying the power spectrum, which really needs a lot of other statistics to be combined in as well. So this is obviously a pretty interesting field, which in the Herschel and Planck era is going to continue to get more interesting, I think, over the next 2 or 3 years. Thank you.
So I'm going to go back to they asked Chris's question in a slightly different context, which is one of the reasons that I got frustrated with the whole dusty galaxy story. And of course, Norm has his own view about how this stuff goes. But the problem is there's such an interesting mixture of kinds of objects that are going to participate, and there's been a certain naivete in expecting that it's a single parameter type of distribution, which is not going to be true at all.
Right.
And one of the standard ways to try and really think about bursting up the things that are actually, in many respects, certainly going to be dominating any aspect of this, is that you have perturbative encounters, which means that it doesn't mean that you have a full-scale merger, which of course can enhance things enormously, but you can just have gas which is sort of hanging out of a central region being perturbed, and so then it falls in and that makes some burst.
Right.
And that's a very complicated statistical problem to nail correctly with any kind of simple tool like the Halo Catch or other pictures without making it more complex. Now, it may be that there is an expression of trying to do that extra complexity. For example, instead of doing something like Chris is advocating, which would be that you were actually trying to take into account the large filament aspect, one could just consider doing a second constraint, which is the neighboring field of the object, which if the density is higher on some larger smooth scale, then it's more likely that there will be a close encounter. I mean, that would be a really simple way to do it. What you would like to do, though, is you'd actually like to do this through n-body calculation, take it fully into account, but nobody knows how to do that, and nobody even knows what they're looking for.
And if
that's what's really the problem. There's no point process that you can easily define for this, and I think this is a situation which makes it quite messy, and actually is great. All of the basic assumption of the 1 and 2 Halo description, because it's saying that there is a whole other physical element that's going on that sets that description.
Right.
So I'm not saying it isn't a gray area, and with the data coming, we have no choice but to actually try and deal with it. But it requires, in my view, some thinking beyond these sort of standard halo-ish box.
So take along the line, isn't it a little disturbing that there's two very non-parallel things that people have to then adjust to come up with? I mean,
What non-parallel thing?
well, you've got the one halo.
Oh, yeah.
Well,
No. Actually, you have to regard this as a tremendous triumph that something as stupid
Was it
as
predicted?
an NFW
No, but
attached onto a.
did they predict this, or was this a fit after the fact, after that parallel was observed?
No. Well, I don't know about the SDSS, but the thing that was quite amazing was when
I would take
the
this.
recognition came that the excluded space aspect of the formation of halos caused the spectrum not to do the NFW-ish steepening up at short scales, but it allowed you to get basically a power law. So where did that come from? Because the power law was not intrinsic. So people had not understood that until that exclusion aspect was at least included in the n-body. It was never really well done in the analytics. And then that was the beginning. The fact that it actually conspired to do your basic argument minus 1.2, absolutely unbelievable.
Right. Well, exactly.
It's a miracle.
So my conclusion is I don't believe it. It's
Well,
just,
no,
it's just
you
a
believe
fit.
you can believe the observation.
No, I believe the observation, but I'm saying that underlying physical model.
No, but anything.
What else are you going to come up with?
And see the halos, so I mean, it's not like a.
You count. You do the correlation function.
I mean, it's not like, you just come in with 3 functions. Anyway, I'm sorry, you should be on.
No. What I was going to say was, the power law is not model dependent. Right. I mean, given you have a power law, you have to come up with components that add to give a
No, but so people have predicted that power law from a 2-halo model.
People measured the galaxy clustering back
Exactly.
in the 70s with very small samples where it was obviously going to be a power law because of the data points.
Exactly, and then they got a power law out of their models, so that's a very different state.
But that power law was observed up to very recently, even with much larger galaxy samples. It was only in 2003, 2004 that going beyond, say, 50,000 galaxies actually brought out small deviations from that.
Yeah, but so I understand. What I'm saying though is that people have adjusted their 2-halo model fit to make it a power law.
No, the power law.
Right? They're trying to fit known data. If they had just said
No,
No,
I don't think that's right. I think it's fairly natural that it comes out. The thing is that
you mean there are no parameters for which you see a big bump?
No, there certainly are.
Well,
but there's a large
Exactly.
range
So
of parameter
picking
space
those-
where the
exactly.
total is supposed
So
to
a
be power.
priori, people should have been able to predict if they understood their modeling that the parameter space would actually pick out a power law for you, and nobody did that.
it was only done numerically.
Numerically, you don't have to
numerically.
you don't have to know about halos numerically. Just put in your stuff and you calculate the power spectrum.
No, I know, but.
So there's no 1 or 2 halo model in
No,
numerics.
but the 1 and 2 halo model is a bit of a misnomer because it's got nothing to do with 1 and 2. There's only 1 halo with assumed profile. What is not taken into account it is the statistical elements of that profile. So what is done is really simple, smooth things. But once you set that that's the statistical formula, assuming everything else follows, it's not like the 2 halo shouldn't be there. It has to be. There's no choice.
Yeah, but does it naturally come out that it's a power law where you haven't
No,
adjusted any of them?
it didn't have to be a power law.
Exactly.
It just happens that that's true. It's one of the weird things.
You're saying it happens from numerical simulations.
No,
not from
but it
any-
also
It's a
happens
coincidence in the data.
with,
Oh, no, I understand. It's also true with the data.
Yeah.
It's a bizarre coincidence in the data, really.
I mean, the main thing about the halo model is they took into account the NFW was put in as the profile, and that helped a lot, and that actually happened relatively late in the story. It wasn't, we didn't use it in the 80s because there was no NFW in the 80s. There was no universality.
Otherwise, this goes on and down.
Sure.
Yeah,
Yeah, that's a good idea.
Just one one question.
Yeah.
Where you showed your square
Yeah.
If you look at a 500 cross 500
Yeah.
micron, there is this term that we have always been worried about, and the data was not good when we did back cross back.
Yeah.
That is, at 500 microns, you have the clusters of galaxies. Right. And then you have cross correlations of the clusters with the CITA.
Are you talking about Siniav's contribution?
Yeah.
Because I'm pretty sure that's negligible if you're looking at the 500 micron plus 500 micron.
So you don't see.
We don't
even
see
in this data.
No, we don't see any need to include that. But I think if you just look at the non-relativistic spectral function of the thermal set effects, you can convince yourself that it's going to be way subdominant. Right. You're right that it's closer to being important here than it is anywhere else. But I don't have a number, but it's not. You didn't account for it.